Welcome to our discussion on limits at infinity, which is normally what we refer to as horizontal asymptotes. Let's start by looking at a simple example. We've got a rational function here with x squared minus 1 over x squared plus 1, and we want to figure out what happens to the function as x gets really, really big. Well, we can look at a table of values, and we can see that as the x values get larger, it looks like the y values, right, the f of x values, are getting closer and closer to 1. And in fact, if you graph the function, you can see plainly that the function levels off at the extremes, right? As we go out to positive infinity and out to negative infinity, the function tends to level off at a height of 1. That's what we would consider a horizontal asymptote. Well, how do we kind of figure this out officially without having to look at a graph? We can tell from the graph what's going on, but we want to be able to kind of figure it out algebraically. Well, we first realize that this is another limit, right? We're taking the limit as x approaches infinity now, instead of as x approaching some number. And we're taking the limit of this function and we're claiming that it equals 1, and in this case it does. Here it is in its general form. It's the very similar limit definition we've seen before, that we say the limit as x approaches a number of a function equals L if the values of that function can get really arbitrarily close to L by taking x sufficiently close to this number, right? It used to be that x went to a, and then x had to be sufficiently close to a. Well, now because we're letting it go to infinity, we're just letting x getting sufficiently close to infinity, which really doesn't exist. So instead we just say it gets sufficiently large. So it's the same definition you guys have seen before, only now we're talking about what happens at infinity. And of course there's no difference when we talk about what happens at negative infinity. The only difference would be taking x sufficiently small, right? Here's another way of writing it. We've seen this before. F of x approaches L as x approaches infinity. This is the less common way of using it, so you really should instead go with the one in green. That's the one that's more widely used. Here's another geometric illustration of the definition, right? That we have this y equals L horizontal line, and as we move off in one direction, the function approaches it, even if it doesn't do it in the other direction, right? We're only concerned, these types of limits are always one directional, right? We're always looking at x going to infinity or x going to negative infinity, and we look at those things separately. There are several different ways a function can approach a horizontal asymptote. It can get to it by getting closer and closer from above. It can come at it from getting closer and closer from below, right? You could have like the natural log function, but the natural log function doesn't actually have a horizontal asymptote, right? But you could have a function that kind of looks like it, that does something like that. And you can see that it's approaching this height from below. This one's approaching it from above, and then this one is oscillating back and forth, but it's leveling out at that number. So the big difference between a horizontal asymptote and a vertical asymptote is a vertical asymptote is something that your function never crosses, right? It always just butts up next to it. Like for instance, this might be the vertical asymptote of just the y-axis, but a horizontal asymptote can be crossed, and in fact it can be crossed infinitely many times, but if it settles out at that height, it still ends up being a horizontal asymptote. Here's our first example that we saw, and we can again remind ourselves that in this case it's approaching from below and it levels off in both directions, both to the positive and to the negative. Which reminds us that if we're looking at a negative infinity, right, what happens at negative infinity? Everything's the same thing, only now instead of taking x sufficiently large, it's x sufficiently large negative. Here's some other examples graphically of what that means, right? Pretty intuitive. We can say that the line y equals L is called the horizontal asymptote if the limits approach it in either direction, right? This is an either or. They don't have to approach in both directions, right? They don't have to approach it in the negative direction and the positive, just one or the other, or sometimes both. As we saw in this example, it worked in both directions. You may recall from other classes that there are other ways to find horizontal asymptotes by looking at the degree of your rational function. So you have some rational function. Remember, rational function just means a function that has a polynomial over a polynomial. And this is just the general way of writing a polynomial. It's a bunch of powers of x with a bunch of leading coefficients. We always put the highest power of x first, so that means this becomes the leading coefficient of the top, and this becomes the leading coefficient of the bottom, because those are the highest powers. And then we had these rules that if n, right, the power of the top was less than the power of the bottom, then it leveled out at y equals 0. If they were the same, it leveled out at a horizontal line that was made up of these two leading coefficients, right? And then if the top was greater than the bottom, if the degree of the top was bigger than the degree of the bottom, we had no horizontal asymptotes. If it was 1 degree bigger, we had a slant asymptote, but that's still not a horizontal, right? And that was the old kind of way that we did it. This new way is really the same thing, we're just kind of formalizing it. We're giving ourselves some steps to calculate them each time. You can always still use these same rules, they still apply. Here's how we could work them out if we wanted to kind of think about what's really happening. If we want to find the limit as x goes to infinity and as x goes to negative infinity of 1 over x, we notice that as x gets larger and larger, we're dividing by bigger and bigger numbers, which means we're getting smaller and smaller numbers, and it tends to seem like it's going to 0. And in fact, if we used these rules, the degree of the top would be 0, right, because it has 1 times x to the 0, and the degree of the bottom would be 1, so the degree of the bottom is bigger than the degree of the top, and it should have a horizontal asymptote at y equals 0, which is exactly what we're going to see here. It's getting closer and closer to 0, so we say the limit equals 0, i.e., right, it levels off at y equals 0. So these rules are interchangeable. So the great thing about math is everything works the same. Okay, so there's a picture of it, nice and simple. This also brings us to this next theorem. You don't have to have this memorized, it's pretty intuitive that if you're taking 1 over any power of x, it's always going to level off at 0 as you go to positive infinity. However, when you go to negative infinity, you have to add an extra little caveat. You have to add the little piece that says x to the r is defined for all x. And the reason why we need that when we're dealing with going to negative infinity is because we're now letting x be a negative number, and we know that we cannot take, right? We can't take even roots of negative numbers. And so if we're plugging in negative values for x and r is a positive rational number, right? A rational number means it could be a fraction. So if r was 1/2, that is actually greater than 0, but that is actually the same thing as taking a square root, and then we would have problems, because as we go out to negative infinity, it's not defined. Okay, so that's the one thing we have to worry about, is if we're going to negative infinity, we have to make sure that the powers play nicely. Here's another example where we could use the same rules that we know before. In this case, we look at the top and we go, okay, the top has a degree of 2, the bottom, right, function has a degree of 2. Since they're the same, we know it's going to level off at the line y equals the top coefficient over the bottom, or 3/5. But what we're really doing is we're taking each polynomial and we're dividing it by the highest power of the denominator. And the reason why we're doing the highest power of the denominator is if the top has a higher power and we divide everything by that, we're going to end up getting zeros in the bottom, and then you can't divide by 0 and we get, bad things happen. So instead you divide by the highest power of the denominator. In this case that's x squared, and they're both the same. And when you divide everything by x squared, you're left with all these bits and pieces. And as we saw from the previous theorem, anything that has 1 divided by a power of x goes to 0. And 2 divided by a power of x is just 2 times 1 divided by a power of x, right? So in this next slide, we can see that we're just kind of using the laws of limits to say we can, instead of taking the limit of the whole thing, we can take the limit of the quotient. Remember, the limit of the top, limit of the bottom. We have that whole thing that the limit of the product is the product of the limits, right? And the limit of a quotient is the quotient of the limits. And then the limit of the sum and the sum of the limits, the limit of the difference, right? So we're using all those laws to basically break it up and take the limits of each individual piece. And then in this one, we took the constant out, right? We took the 2 out. And what we've done is we've broken it down so that we're left with a bunch of limits of just 1 over powers of x. And according to that theorem, we know that if we're going to positive infinity, those all go to 0. And so 0, 0, 0, right? This technically should be 2 times 0, but we know that's just 0. And then it ends up just being 3/5 like we knew it should be. Okay, so there's the technical way of why this works, and then there's, hey, I remember this, it's just about the degrees of the polynomials, and you can always use that as well. If we did the same thing for going to negative infinity, we would be okay because it's being squared, and we don't have to worry about taking roots. And we'll see that the exact same thing happens, and it levels off at 3/5 as well. Another example, this one's really good because when we're looking at this, what is the degree of the top? Right? What is the degree of that top polynomial? Some of you might think the degree is 2, and it isn't, because this whole thing is being squared. So the degree of the top is actually 1. And what's the degree of the bottom? It's also obviously 1, right? X to the 1. And if the degrees are the same, we know that it has to level off at y equals, right, a over b. Well, b is pretty obvious. That's 3. But what's a? What's the coefficient of that term? Square root of 2. This is how we would do it the technical way. We would divide everything by x, but when we divide the top by x, to put it inside the square root, we actually have to divide by x squared. And that's where we get all of this stuff, and look at that. We get the exact same answer that we got from just using the rules about degrees of the polynomials. Now, to go in the other direction, right, to go to negative infinity, we have to remember that as long as x is greater than 0, the square root of x squared ends up equaling a positive x. But if x is less than 0, when we square it, we get a positive. When we square root it, we still get a positive, and we end up getting an x that is the opposite of what we started with, right? So this doesn't mean that we get a negative answer, because we all know we get a positive number out of a square root. What we're getting is the opposite of the number we put in, right? So if we start with, let's say, x equals negative 3, we put it in here, we get the square root of 9, which equals 3. Can you see how that is negative of what we started with, right? It's negative of negative 3. So that's what this is saying, that the answer we get is always the opposite of what we started with. And when that happens, when we do this whole dividing by the bottom power, we have to realize that it introduces a negative into the equation, and we end up getting negative square root of 2 over 3. You could also just look at this logically, right? And that's the better way that I like to do it, because this seems to make my head hurt, and it's confusing, and I know that this is something that would be very easy for all of you to forget. So instead, still use the same normal technique of, what's the degree of the top, degree of the bottom. Okay, so they're the same, so we know it's going to be square root of 2 over 3, more or less. But you always have to remember, okay, when I'm doing negative, though, things can be weird with square roots and stuff like that. As you go out to negative numbers, what happens to the bottom? Well, I'm getting bigger and bigger negative numbers, right? So as I go out to negative infinity, the bottom of this fraction is always negative. But as I go out to negative infinity, they're becoming squared, which are positive, right? And taking a square root, which is positive. So I end up getting a positive number on top. And therefore, this thing can't level off at square root of 2 over 3. It has to level off at square root of 2 over negative 3, which is really negative square root of 2 over 3. Okay, so that to me is the better way of remembering that when we go in the negative direction for this particular example, it's going to be a negative number. This is just walking you through that same logic. And then here is the graph of the function, verifying that we do in fact have two horizontal asymptotes, one in the positive direction and one in the negative direction. Okay, the last idea we want to talk about is, what about infinite limits at infinity? Meaning, if we're going out to infinity or negative infinity, we get an answer of infinity or negative infinity. So we can have that combination. That's not a problem. But what does that really mean? Well, here's an example. If you take x to infinity or x to negative infinity of x cubed, you can see very easily that it just gets super big, either in the positive or negative direction, depending on if you're putting positive or negative numbers in. And you get a function that looks like this, right? So if we say the limit as x goes to infinity of something equals infinity, that just means that as we go out to the right, right? So as x goes out to the right, the function blows up, right? That's limit as x goes to infinity of f of x just equals infinity. And then of course, if f of x gets super small, then that means the limit of f of x as x goes to infinity equals negative infinity. And of course the other two for going to negative infinity, you get the idea. It's the same concept. Pretty basic, easy stuff. Try not to overthink it.